Officially 11. I don't know what makes it official. My phone says it's 11. Just taking its word for it. Thank you everybody for making it online one more time. I don't know if we're ever going to get to meet in person. I hope so. Let's see how it goes on Thursday, if there is no further disasters. Um, Before we start on today's topics, any questions about what we've done so far, about the course, anything? Okay, not hearing any, so we're good to go. Oh, and I decided to change my background to be more seasonal. It was supposed to start snowing at 9. I don't know if it's ever going to snow, and I'm okay if it doesn't.
I
But
see
anyway,
it. I see it snowing right now out my window.
it's snowing here.
It's pretty.
It's not knowing where I am.
Oh, okay. It's very light.
Wait, are you still in New York?
No, I'm in Auburn now finally.
Ah,
But
okay.
in New
That'd be
York,
cheating.
it would be definitely snowing.
Yeah. No, I don't see anything here. Oh well. Hopefully it will not come. We can do without. All right. Let's see. Let's start from here. There. You remember what we discussed? We looked at the bisection method and and will keep coming in. Hope everybody's here now. We'll make automatic um, uh, admission. Anyway, um, and after looking at the bisection method, we thought about an idea that is take given 2 points, take the straight line that goes through those 2 points and the function values, and assume or pose falsely, because if it was a straight line, we wouldn't need to do the numerical solution of the equation, that our function is a straight line. Um, Again, the second method is um, a variant, different strategy on the same idea. And then we find the zero of that straight line, which is trivial, and that's our next point. With the difference between the two options, the second method and the regular false or false position method, being which point we throw away. So you remember what we've already said, that the risk of throwing away the oldest point is that the root may not be bracketed anymore. The risk of always keeping the root bracketed is that you may get stuck on one of the points where may not move, and it may not be actually a point that's really close to the zero. So let's see in practice how this works. I should actually get into my Zoom here to see how well it shows. Okay, it's visible enough. All right, you remember this Mathematica file. Oh, I should ask, I'm guessing nobody's going to volunteer any actual answer, but is everyone okay with what I've been showing for the little programs and codes? Can everybody follow? I know there is somebody that doesn't have coding experience. I hope you've looked at the tutorials that I recommended. If
Some
you get in trouble with the coding, you'll have to do coding for the first homework that I'm going to assign this week, depending on how far we get today.
Is the do loop in Mathematica like a while loop? And is there a condition on the um
There is
ending of it?
yeah, Mathematica has a while loop. Here I'm just doing a do for 10 iterations,
Oh, I see. Okay.
but yeah, I could also set up a convergence condition.
Yep.
Say while this quantity is larger than this quantity that I define as convergence criterion is larger than the number I want, keep going.
Yep.
Um, if anybody doesn't know how this works, is that the encoding, this is of course useful for this method where we keep doing the same thing over and over, just changing the points. The idea is to write the instruction once and then tell the computer in the programming language, keep doing this thing until I tell you to stop. And you can tell it to stop in different ways. You can say with something like a do or a for loop, do it this many times, and you set the number of times ahead of time. Sorry for the um, bad choice of words. Or you can say, do this until this condition is met. And then you have to set up the condition depending on your problem. All right. So I've run this ahead of time, so I'm not going to run it now, but here's what we do. We say, let's just go for 10 iterations. Here is an empty table that where I'm going to put various numbers so I can plot them later. And I'm going to start with x1 and x2. And my f is what I call f4 in my example. So it's again x squared minus 2. I'm again going to try and calculate square root of 2. Okay, back where we were. Should I use the cursor? Not being very smart. Okay. So my starting points are 1 and 2, which obviously bracket the solution. Then I calculate y1 and y2. I also calculate the derivatives of the function, and they're not needed by the method, but I'm doing it so that I can see how the derivatives. I'm actually not plotting the slope of the second line, but sorry, you can see my hands. The slope of the second line, but if the 2 points converge, get closer and closer to the solution, then the slope of the second line is going to be equal to the derivative. That's something that we could check. All right. Then here is the approximation of the derivative, which I just take as a finite difference between the values of the function, the values of x. And then I say my function is, the value of my function is equal to the value in point 1 plus the derivative times x minus x1. And I set this equal to 0 and solve for x. This is trivial, and find x3. And then calculate the new point, the value of the function derivative in the new point. And then I do, if I do this check, it's another fundamental logical construct that you'll have in any coding language. If the product of y1 and y3 is positive, that means I have the same sign. It doesn't matter, it could be both positive or both negative, but I know they have the same sign. I'm doing false position, meaning I'm going to keep the root bracketed. Therefore, I need to replace x1 with x3. So the new point as x3 gives me a function with the same sign as the point x1, then this is my new point x1. Otherwise, so this comma here is what will be else in a logical construct. And Mathematica is very funny in the way instructions are inserted. So you have, if you use Mathematica, you have to, it's rather different from most other languages in terms of syntax. Anyway, so this is the alternative. Then if this is not true, that means that y2 and y3 have the same sign, and therefore I'm going to replace x2 with x3. And then put the numbers in my table and cycle. Again, I'm not checking the option, the possibility that y3 is exactly equal to 0. And you typically don't do that. So you'll notice what I'm, it's easy to see here, but what I'm using is some type of algebraic system that, or algorithm that will always, if I start with x1 and x2 being rational numbers, this will always give me a rational number. If I know that the answer is not a rational number, as I do in this case, this method will never give me the exact answer. Will give me an approximation as good as I want, as long as I can represent the numbers with sufficient accuracy, but it will not give me any rational number. But I can always get as close as I want to an irrational number with a rational number. Sorry, tea was getting cold, and cold tea is not terribly attractive today. All right, let's see how it goes. Here's our table. Here's the number of iteration. Here's point x1. Here's point x2. The value of the function, the point x1. The value of the function, the point x2. And here are the values of the derivative. So you see what is happening. I start with 1 and 2, then 1.3, 1.4, 1.411. So these are the digits I normally remember of square root of 2. I wonder why do I remember digits of square root of 2? I don't know. It just happened. But anyway, this is the answer I found with a find root of Mathematica that will give me a pretty good approximation of the root. And you see that after 6 iterations, I'm getting the same, no, 7, the same number. And this is in fact the error, how far from 0 my function is. But you'll also notice that one of the points never moved. And it wasn't because this point was close to the correct solution. That point was not particularly close to the correct solution. I mean, 2 is not a terribly good approximation for our 1.414 blah blah. But that point just never moved. And indeed, the derivative, well, you know what the derivative of square root of x is 1 over 2 square root of x. So we can check the number, but that's what I'm getting. And it's changing in one of them, it's not changing in the other one. Well, before we get to that, let's go back to our first example, the bisection one. How did it go here? Well, after 10 iteration, the error was still, the error is that here I'm defining the value of the function. So the absolute value of f of x should be 0. Is still 10 to the minus 3. I'm taking the worst one because I I can take either, but you see it's still order 10 to minus 3 or 10 to the minus 4. Actually, when I run the algorithm, I calculate the function, so I can always take my best as my best approximation of one that gives me the smaller value. But you'll also notice that this one hasn't moved in several iterations. Now, if I'm interested in the value of x, here is how close I am to the value of x. And you see that I got the first 2 digits right. While with this method, I got the first, however many these are, 6 digits right after 7 iterations. The value of the function goes down to 10 to the minus 6. So that tells me, at least in this case, I don't know if that's I don't know yet if that's a general property, but at least in this case, this method is doing a better job in the sense that it's getting close to the solution faster. Now, let's look at a couple of plots. Don't mind too much. So this is a place where MATLAB is a lot better. I just had this done in Mathematica, and that's why I'm showing it in Mathematica. But doing a plot is so much easier in MATLAB. And that's the reason why I thought MATLAB would be a better choice. Okay, here I'm showing the points x1 and x2. Okay, this one is x1 and x2 versus the number of iterations. And you see that x2 is pretty flat after a few iterations. It goes to the right number. And here is the value of the function calculated in x2 and calculated in x1. The one in x1 goes to 0, the other one stays there at 2. And chances are, well, I don't want to get that deep, but in this case, it would pretty much never move. And here's the calculation of the derivative. Okay, the reason why the second point doesn't move is depends on the shape of the function. If you can plot the function, you can possibly get an idea of whether both points will move or not. But it's kind of a little tricky, maybe. So it may not be. It may not really be worth doing. On the other hand, this still worked, and it went faster than the bisection method. That may be good enough for our applications. Let's say we want 3, 4 digits of accuracy on our solution, and this function is very expensive to calculate. I'm not going to care too much if one of the points is not close to the root. I know that one of them is, and that's my best guess for the solution. So it's not a terribly bad method. The next option is the second method, which, as you remember, is the same exact thing with the only difference that we're always throwing away the oldest point. And I've said more than once what the risks are. So here I made x1 equal to 2. Is that what I did before? It doesn't really matter. I thought I had no, okay. I switched the points. I don't know why. Yeah, maybe because I wanted to throw away x1 immediately. But anyway, the coding, it's the same function, square root of 2, or rather square root of x minus 2. And the syntax and the coding is exactly the same. Um, so I do the same thing, calculate an approximation of the derivative, and then calculate the new point x3. That is the point where the straight line that I'm using to approximate my function goes to 0. And here I don't have any condition to check. I'm always going to throw away point 1. So my new point 1 is going to be what was point 2, and my new point 2 is the one I just calculated. So I shift the points down or up in counting. What was earlier point 2 becomes point 1. The new point, which I was calling x3, becomes x2. And on the next iteration, I'm going to throw away the new x1, which was the second point I started from. So after 2 iterations, I'm guaranteed that neither of the initial points is going to be there. Okay, and then I do the usual thing. Let's see how this goes. And you can see this looks, well, for one thing, both points are clearly moving closer. Here I have the value, sorry, here is the value of the function. So after a couple of iterations, they're both 10 to the minus 2, then one goes to 10 to the minus 6, and then the next one is 10 to the minus 10, and wow, this goes down pretty fast. And at this point, at this point it gets stuck, and that's because the uh, numerical representation of the numbers that I'm using doesn't have enough accuracy to go any further. So I keep finding the same points, but that's okay. I mean, after 6 iterations, I will have one of the points that's giving me a value of the function that's 10 to the minus 16. That's pretty much machine precision. So that I know that's as good as I can make it. And if I'm happy with 10 to the minus 6, I need 4 iterations. Or 5 for 10 to the minus 10. This goes down pretty fast for the value of the function. Here I'm not plotting all the values of all the digits in the values of x, but you will see that those get close to the correct value, the desired value, pretty quickly. Okay, what else? Yes. One, let's see if that happens here. I don't think it does because of the way the function is. Oh, yes, it does. At this point, both values of the function are negative. So the root is not bracketed. And you can see it from here, 1 and 1.3. That actually tells me, well, but what if I'd started from 1 and 1.3? Will this have worked anyway? And the answer is yes, because in the next iteration, I get 1.42, which gives me a positive value of the function. So one advantage of the second method, where I'm always throwing away the oldest point, is that I need to start with an initial guess, and I need 2 numbers, but the 2 numbers don't need to bracket the root. Is this good or bad? Well, matter of a matter of taste. In fact, I may start bracketing the root, and I may lose the bracketing in some iteration. As I said before, good reminder, if the root is bracketed uh, and the function satisfies all the requirements, that is pretty much it's a continuous function, you're guaranteed that you're going to find a zero. If you accept not having the root bracketed, then you may or may not converge to a root. The method may just take you far away from the root and never bring you back. And that can happen. It's typically what happens for oscillatory functions. So if you have something that goes up and down, you may be in some place where the slope points away from the root. Let's see. I can make an example here. Oh, sorry, something in the chat. Let's see, I need to. So then I can share from here. Share content screen. Yeah, start broadcast. There you go. Okay. Go away. Thank you. Let's see. This is more than 100%. Okay. Let's say I have some function. I could have made this bigger. Start over. Sorry about that. Thank you so much. Better. Okay, finally. Let's say I have a function that goes like this. So it's going to be pretty easy to find. I'm just taking a wild guess, two initial points. Let me mark them here. And then I do my straight line through those 2 points. That's actually taking me away from the root, because it will tell me our next best guess is this point here. Oops, sorry, that's the thin one. Which is clearly farther from the root. Will this converge? Doubtly. The function oscillates so much that chances are this is not going to work. But the other version, the false position would, because you're keeping the root bracketed. It may not do an awesome job, but it will converge. Any questions? Okay, now, oops. Sorry, one moment. Did I close the thing I needed? Pretty sure I did. Okay, no problem. I have a Ah, no, I didn't. Maybe I did. Ah, okay. Sorry, what I'm looking for is the correct spelling, which I'm not very good at spelling. You may have noticed. All right. Let's get to today. The next idea is, well, let me be more precise. I'm giving you, describing these methods in a way that is easy for me to understand um, and keep um, in a nice rational sequence, but that's not necessarily the way or the order these methods were developed. So my um, line of thinking going from bisection to Newton or Newton-Raphson is saying first we bracket the solution, and then we say let's just take the point in the middle, and then we um, observe what if we bracket the solution, we have additional information that's the value of the function. So let's take a straight line between those 2 points, and then I say, by the way, that straight line becomes the derivative of the function when I get close enough to the root of the function. Then why not start with the derivative? But that's not the way this happened historically, not necessarily. Um, at any rate, so this is also very often just called Newton method. I don't know who this Rapson person was. I've heard of Newton before. You probably all have. I don't have any um, historical biographical information on Mr. or Dr. Rapson. Sorry, but anyway, if you see the name Newton method or Newton-Raphson method, chances are they mean the same exact thing. Okay, so the idea is I'm going to use the derivative of my function, not just the value of the function. That requires two um, two additional um, that requires something more of my function, and hopefully that's obvious. The requirement is you need to be able to calculate the derivative, and in order to do that, you must, of course, first require the function to have a derivative. That means my function must be not only continuous, but also smooth. Where smooth, when I took calculus, that was in a different language, but so a different word was used. But in general, when I hear smooth, I understand that it's got all the derivatives that I need. So let's assume that my function has at least a couple of the derivatives, so we can do all the things that we need to do. In general, that's true for um, functions that come out of physical problems. You have to solve an equation, a dispersion relation for some frequency or whatever. yeah, that's probably going to have, it's going to be some, maybe a complicated transcendental function, but it's something you can take derivatives of. I mean, the derivative may, the function may diverge, the derivative may go to infinity somewhere, you may have all sorts of other issues, but the derivative is going to exist, which is what the Newton method assumes. So let's say that we're trying to solve f of x equals 0. So let me just make sure. Oh, wrong button, sorry. Okay, looks like it's updating better today. And let me call the solution, what I've been using, x0, can call it anything. Let me call it alpha today. Okay, what happened there? I guess I shouldn't be calling it alpha. I'll call it x0. So that's the exact solution. Then I can say that this is not the only way to introduce the method, but one way to do it is to use a Taylor expansion. There is a catch. It's an important catch. Nobody's asked me yet. I mean, nobody's asked me anything much yet. So I hope that's not a bad sign. But I'm going to assume that this condition is satisfied. Now, that is not a trivial condition. I hope that I don't know if you can see how much I'm actually asking of my function. So let's do a little aside. What does this actually mean? I could have a situation where my function does something like this. I don't think I have a curve that will do that. No. So in um, it may be that my function has a double root in some point. So if that is the case, then the graph is going to look something like this. And for one thing, I'm not going to find a bracket for this type of function. But that function still has a 0. And in this case, if I'm looking for a 0 numerically, I may be in trouble because I may not be able to I may not be able to find. There is not going to be anything that tells me there is going to be a zero in this region, unless I know from somewhere else that there is going to be a zero in a certain interval, and I expect that to be a double zero. That may be um, again, if it's a problem coming from physics, you may just know, but this function will go to zero here, but I know that it's going to be a double zero. So that sucks. And dealing with this type of problem is done in a different way that, no, sorry, that we're not going to get into now, and maybe we'll do some time later. Haven't quite decided yet. But there is also another option that my function does something like this. So that's again a multiple zero, but that would be like a triple zero. So the function still changes sign. Then by bracketing and false position, second method, they're all going to work. Newton method will not, because my derivative is going to go to zero when I get close to the point. How do I know if that's going to happen? Again, either you know it from the problem, you know something about the problem, and you know what to expect, or you're in trouble. There is no way. Uh, I mean, you may observe it from um, the behavior of the numerical method as you're trying to solve the equation. You see that something goes wrong, and uh, you may be able to figure out, okay, why?
In practice, how might we know that we're maybe hitting on a function like this? Like, would it um be because we're assuming that the derivative evaluated at the point is non-zero, if it actually is zero, then we just get uh zeros as our approximation, or like nonsense, or I don't know what the
Um,
computer
so
does.
yeah, we'll we'll see it shortly, but um, what's going to happen is that you're going to have a coefficient in, or one of the numbers that you need in the Newton method that goes to zero, and you're actually going to divide by that number. So that's an indication. Okay, my method is moving very far away from where it was, and the value of the function was pretty small. So that's telling me that there may be something going wrong there.
Okay.
The good news is that there are pretty simple fixes to that. But let's look at and I guess I can um, tell you about that in a moment. But let's look at the Newton method first. Um, so I used x0, right? So let's say that, well, we'll look into that later. I'm going to say that f of x, if I'm close enough to x0, very important, if I'm close enough to x0, is going to be um, equal, well, actually, no. I mean, this is true, but that's not what um, I'm writing it backwards. Sorry, got ahead of myself. All right, so I want to find f of x0, which is 0, and that's going to be equal to f of x, where x is my current point, plus, let's see, x0 minus x, because I'm centering in x, times f prime of x. Um, and then there is going to be um, x0 minus x square this I don't really need for the method. Um, let me call this, just give it a random name. And let's say it doesn't matter which one is larger. So that's, I guess that's called Lagrange theorem. What I'm saying here is that I can do a Taylor expansion and I could still use the point x and then the Taylor expansion goes to infinity. Or I can say, well, there is going to be, if the function is continuous and its first and second derivative are continuous, there is going to be a point between x and x0 such that if I calculate the second derivative at that point, this is exact. I don't actually need it for the method, but I sort of need it to evaluate the error. Indeed, what I'm going to say is, um, let me set this equal to 0, and let me just keep the first term, just a linear term. So this is going to be approximately equal to 0, and if I assume this to be a good approximation of my function, I can solve for x0, and x0 is going to be approximately equal to, I need to divide by, so I'm going to have f f of x divided by f prime of x. And you see what is happening here. I'm dividing by the first derivative. So if the initial approximation is, sorry, if the first derivative is going to 0 at the 0 of my function, then I'm dividing by 0, then my method is going to send me very far from the solution, actually. The other important point here, this is an important point for this method and in general single point methods. This is going to work really well if this works. So type. So that's true if x and x0 are close enough. Should be this thing. Now, close enough is not a terribly accurate mathematical definition, and I'm not giving you a number, and I can't give you a number. It's going to depend on the case. But the point is, if the function is smooth enough, I do a Taylor expansion, and I know that if I'm close enough to the point I'm looking for, then only keeping the first order in the Taylor expansion, which is what I'm doing with the Newton method, is a pretty decent approximation of the function. Now, if I'm too far, then this may not be a good approximation at all. And that I'm going to find out because my method is not going to converge. Okay, so let's see. Let me just I'm not sure what happens if I do two shares at a time, so let's keep it simple. And let's go back to our Mathematica file. I'm sorry, I think I didn't show you the plot. So here was here I'm plotting just the last number since I'm not bracketing. Back to the second method. I'm sorry about that. I meant to show you this. And you see that the point moves, first goes up, then goes up, goes too far up, and then comes back down, and then it's pretty much flat. And here is value of the function. It's negative, it's positive. Then it gets pretty close to zero, and it doesn't matter if it's positive or negative. And here is for the derivative. Okay, Newton method. All the same thing, except that now I have, I'm not going to need the point x2. I'm just going to use the point x1. I started from 1. The function is smooth enough that 1 is close enough. It's going to work. Then I'm calculating the value of the function. And then I'm calculating the value of the derivative. And then I'm saying my new point is x1 minus y1 divided by y1 prime, the derivative of f calculating the point x1. And I'm calling this 3 just because I had it set up this way. It doesn't matter. I could call it 27, or I could call it z instead of y. But that's the new point, and that's the new value of the function. And then I calculate the value, I calculate the derivative, and I calculate the next point and keep going. I don't think at this point there is any way to guess how well this is going to work. Going to do a better job than the second method or not. One thing you can guess, it's probably going to do a better job than the bisection method because again, I'm not just taking the sign of the function, but I'm taking the slope of the function. And I'm not only taking the value, I'm also taking the slope, which is sort of what the second method was doing in an approximate way. So I think I'd be surprised if this method, when it works, didn't do better than bisection. And here's our table. Here's number of iteration, value of the point x, and value of the function. And you see this goes down like really, really fast. My value of the function was order 1, 10 to the minus 1, 10 to the minus 3, 10 to the minus 6, minus 12, and then goes down to machine precision after 4 iterations. And if I plot it, blah, 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 so that's, again, the value of x goes from 1 to 1.5, and then goes down, it's flat. And the value of the function, negative, positive, done. Okay, that seems pretty good. It's like a pretty good method, except you can pretty easily find ways to make this method fail. if you don't start from a good approximation of um, a good approximation of the solution. Questions?
These methods can also work if our function is more maybe abstract in the sense that like maybe you had a computer program that you're running that
Mm-hmm.
gives you a number as a
Yeah.
result, and you can then send that result to a root finding algorithm, and it will give you updates that way too, right?
Yes. No.
In that case, it's harder to make sense of like the Newton-Raphson method because it's the derivative of a function that is more abstract like that is a little bit weird to think about, but
Yeah. Um, so indeed, when you use this in practice in applications, you'll have some type of code probably that will you code this function any of these algorithms in some way that says call this function and use the number that it returns. And that for a Newton method, you may to say call this function that gives you the value of the function, the value of its derivative, and you have no idea of, I mean, the external routine, the one that calculates the zero, has no idea of um, when or how those numbers are calculated.
mhm.
Um, so this may be coming out of wherever. You don't need an analytic expression. You just need something that gives you a number, and you don't need to know where the number comes from, or two numbers in case of the Newton method.
Yep.
Does that answer your question?
Yep, definitely.
Okay. All right. So there are a few more things to look at here. There's a lot more things, but um, debating which one to do first, because the one I wanted to do first is not going to fit in the time we have left. Uh, so first thing we can look at is let me share from here now. No, I don't need to share for now. Um, is what to do with the Newton method if if you run into any trouble. Um, so this is a little tricky, but one way to efficiently use the Newton method is the following. First, you bracket the root, which is not required by the Newton method. Then you take one of the 2 points, intuitively the one that gives you the smaller value for the function, and use the Newton method. Then you check, so you find a new point x3, check if the value of the function, um, so if this new point still gives you a bracket, or and if the value of the function decreased. And if not, you discard that iteration and use bisection instead. Then either way, you have 2 new points that are still bracketing the solution. Do a Newton iteration. Say, is this taking me closer to the root? Is it taking me out of my initial interval? if it's taking me out of my initial interval, something is going wrong, and maybe we're sharing. Maybe a function like the one I was showing earlier. Like this thing here. So let's say my points are one here and one there. So I'm bracketing the root. I take the derivative here and it goes who knows where. So I see now this point, this new point, it takes me very far away from the initial bracket. Let me do a bisection step. But maybe I end up here and then I take the derivative and go down and actually come close to the correct solution quite a bit faster. So this type of method, it's pretty decent. It's guaranteed to converge still with all the assumptions of the case. And it may be slower than the Newton method itself, but worst case scenario is going to converge. So it's going to give you a correct root, and it's going to do it as well as the bisection method would. Best case scenario is going to do as well as the Newton method. And that's a pretty robust way to deal with pathological functions like the one I'm showing here. There is something more, actually, yes. Okay. So we're going to do this on Thursday. We're going to talk about a convergence rate. That is how quickly a function goes to, sorry, a method finds the correct solution for my function. And we've seen a few examples. So this one, it's doing looks like a pretty decent job, but the next ones are doing better. So okay, that's this one that's broken. So this one is going down to 10 to the minus 8 in 10 iterations. The next one is going to go down to 10 to the minus 16 in 6 iterations. The last one is going to go down 10 to the minus 16 in 5 iterations. So this is for one case. You may, it is a legitimate question to ask, which one is best. Is this always going to go this way? Meaning, is the Newton method always to be faster? Um, the the correct answer is maybe. So once you're close enough to the root, and these approximations, the second and the Newton, the Taylor expansion that we use for the Newton and so on, are valid, are good representation of the function, then you can guarantee that the Newton method is going to converge faster than any of the other methods that we've seen, and we'll do the algebra. However, you also have to take into account the fact that the Newton method doesn't only require you to calculate the function, but also its first derivative at each iteration. So in each iteration, you have to calculate two values. And in general, it is safe to assume that the cost of calculating the function is not too different from the cost of calculating the derivative. So I'm pretty much doing double the work in each iteration. So another way to decide which method is better is to look at how quickly is it converging and how much is it costing me, and put the two numbers together and get a one figure of merit that will tell me, which one is least expensive. So that is pretty much all I'm going to say about root finding methods. So these are the ones we're going to look at in detail, and we'll talk about convergence on Thursday. In see, yeah, that we can do. You may wonder, okay, but what's in this find root? That's no, if you can. No, it's not. Sorry. Okay. So if you look at the details, don't care about the examples. It's not going to tell me about the method. So they did. So in general, the another thing that's really terrible with mathematics is the help. But okay, maybe yes. It's I'm going to tell you something about the method, and it says here the default is the Newton method, and the next one is Brent method, another super classic method. Or you could use second, and you can specify it. I don't even know what this one is. So in general, these routines will tell you what they're using. You may have to dig a little bit, but it may be that they're using methods that were not talked about. So what happens here is that you can do additional things with the information you have. And the next guess could be, well, but if the Newton method kind of works well by taking the first derivative, what if I take the second derivative too? Or maybe I use 3 points and I put a parabola between the 3 points. Is that going to work better? The answer is not really. But you may think of other ways. And actually, the Brent method is, as I said, a classic that requires to bracket the the root, and it's going to work. It's going to go pretty quickly. You see that this does 16 evaluation of the function. The second needs 27 to find the same accuracy. So it converges pretty fast. How does it work? I don't want to get into that level of detail. And actually, that's something we're going to do for other things too. My hope here is to give you enough information that you can, enough understanding that you can go and dig for a more complicated method. If you need to know, you can understand what it's doing. You have all the basics that you need to understand what any more sophisticated method will do. But the time it takes to go through one of these methods is probably a whole lecture. It's not really worth it. Also because then the coding becomes a little more cumbersome. So there you can use the built-in functions, and you can find it online or in Mathematica or MATLAB or whatever. But hopefully now you can have the understanding of seeing what do they do and how do they work. But notice that in general, the default is still Newton's method. Actually, the way this is built, the way Mathematica does it is to use Newton method if you give 1 point, and to use, I think it's going to use second if you give 2 points by default. So you can easily pick which one you want, or you can just say, yeah, this is the method I want. Okay, so that's that. For the case where, since we have a couple of minutes, I don't plan at this point to look into that directly, but I'll just give you general idea. If your function is, why did I stop share? I do not know. If your function is of this type, then, and you know from somewhere else that that function is actually going to go to 0 there, then what you use is find the minimum, a function that will find the minimum of f of x. An algorithm will find the minimum. And and you can see, should be able to see pretty easily how you will do that. Again, you calculate the derivative, you always go down the slope, and that will take you to the 0. At least conceptually, it's not that hard. And it's a little more messy than that, of course. If you have a function like this, yeah, you go down the slope. Okay, I found the minimum, but that's not a 0. So what do I do now? So those are a lot harder to deal with, and there's no general method guaranteed to work. Another thing, we'll touch on that at least a little bit. But another thing that may turn up in some physics problem is what do I have to do? How do I solve the problem where I'm not finding, I'm not looking for a f scalar function of x, scalar value equal to 0, but I'm looking for something like vector f of vector x equal to 0. That's that's again a very hard problem. But in general, you can well, in general, actually, what's going to work best is the Newton method. So it's a pretty powerful method. Okay, there is a couple of minutes left. I will not get into anything more at this point. Any questions? Anything? So again, for everybody, if you have any issues with coding, you're worried, um, check the tutorial. It's a 2-hour tutorial on MATLAB. I think it's pretty good, but you know, I learned coding a while ago, so the things that it's saying are okay. Yeah, I know this stuff. If you see it for the first time, may not be as good as I'm thinking. Don't wait to let me know that you're having issues. And I hope everybody got your potato field, and I'm going to look at those and think I can assign the first homework. Um, I've actually not written it yet, but what I think I'll do, I'll look at what you came up with, and I'll ask you to solve the physics problem that you suggested in the potato answer. Find a numerical root for that. So set it up as a numerical problem and find a solution for that. All right. I will see you hopefully in person on Thursday, but let's see what the future brings. Take care, everybody. Stay warm.
Thank you.